Hello, everyone. Thanks for joining us today for the PCIe Technology for Long and Short Reach in Automotive Applications webinar. We'll get started here in just a moment. Hi, everyone. Thanks again for joining us for the PCIe Technology for Long and Short Reach in Automotive Applications webinar, part of the PCI-SIG Automotive Webinar Series. We wanted to take a moment to introduce you to today's presenters. We have Hope Bovenzi, Head of Marketing at Astera Labs, Anwar Sadat, Product Instruments, and Ido Cohen, Director of Strategic Innovation at Valens. Now, I'll go ahead and pass it over to the presenters to discuss today's agenda.
Sounds great. So for today's agenda, we are going to go over some of the automotive PCIe technology opportunities and really discuss what the benefits are of PCIe in automotive. And then we'll go into some of the long reach applications, so inter-ECU connectivity over cables, some of the protocol advantages between inter-ECU connectivity, as well as some of the automotive connectivity challenges that arise. Beyond that, we'll also go into automotive PCIe technology short reach applications. So within the ECU connectivity, go into some of the signal conditioning, and then we'll have a summary at the end of the presentation. So to begin with, let's go over just kind of a framework of and level set of the market right now. So as you may be aware, the the architecture within the automotive world has really shifted significantly over the past 20 so years. In the early 2000s, you had a couple of, or at the end of the 90s, you had a couple of ECUs within the car, 2 to 3. And as we progressed into the 2000s and early 2010s, we were reaching this 30 to even 100 ECUs. I think in the early 2010s, it was around 120 ECUs on average per car. And so what this evolved into was really a domain controller type of architecture that was required. So being able to control different domains of the car, whether that is infotainment, IVI, ADAS domains, powertrain domains, or even other connectivity domains as well, or body control as well. So this is kind of what has shifted into today's architecture. You're seeing this in a lot of automotive OEMs right now, but this is becoming more and more complex still, and cabling challenges, as well as just the vast amount of control and processing power that's required within the vehicle today, domain controls will no longer be sufficient. And so we're moving into something called zonal control, where instead of having a domain controller for different types of domains within the car, such as infotainment, you're going to have a zonal control. And so you can kind of see in this picture here on the right-hand side from Texas Instruments that within a certain region of the car, the zone of the car, that's what will be controlling those those types of sensors or other ECUs, other processors, really to streamline the complexity in the automotive architecture there. So honing in on this zonal control architecture, the amount of data, as we've talked about, is just growing exponentially. It's going from, we've seen, 100 megabits to now gigabit architecture, and shortly that will be move into tens of gigabits as well. And latency requirements are just going to become more stringent, moving towards the tens of nanoseconds. And like I said, the domain control architecture of the car will not be able to meet these performance requirements. It will just become too complex, and it will become inefficient. And that's what is driving that need for the shift to zonal architecture. Advancements in processing capabilities in the vehicle network, the in-vehicle network, is really driving this transition to something called a central computing or a central gateway. And the low latency requirements for zonal vehicle architecture will just continue to increase. So let's hop into how PCIe kind of fits into this picture as we're moving into the zonal architecture of the vehicle. So this is going to be talking about PCIe technology over long-reach cable applications. And I'll talk a little bit about, I'll preface a little bit of the long reach as well as the short reach here, just to kind of set the stage. So for PCIe, why is PCIe going to be the connectivity backbone for automotive? So I'm just going to click through these real quick here. Really, it's a natural I/O bus, and it's already available on a lot of SoC controllers today. That shouldn't be a surprise, but you look at your processors, whether in ADAS, as you can see on the top hand of this picture, or in the bottom corner here with the ADAS or IVI SoCs, as these are being connected, there's already natively PCIe on these SoCs. Furthermore, it's an open standard, huge ecosystem, and it's extremely low latency, has extremely low latency of hundreds of nanoseconds. It's also very reliable, and it's scalable. We talked about how we have moved from 10 megabit, 100 megabit to a gig, and we will soon be moving further beyond that. This protocol will help scale that transition into the higher gigabit speeds, and it can support up to 16 lanes. This can also support multiple topologies, and we'll talk a little bit more about that in a sec. And this picture is just a preface of the different types of applications and topologies, going from chip to chip, backplane or over cable. It can be used in point-to-point or switched architectures. And it can also expand from I/O interface to system interface, so such as NVMe SSDs, and no protocol bus converters are required in this using PCIe here. So beyond that, a little plug for CXL. PCIe-based CXL unifies interconnects. We're seeing this more and more in the data center applications, but this could also be an application in the automotive world as well. So honing in on this picture here, we have, and in the previous picture, you saw this as an ADAS controller going to an IVI controller. Really, we don't need to even segment that into the different types of domains. These could just be two central computers within the vehicle talking to one another. So these are just some examples. But what I want to talk about here is some of the signal conditioning supports that can happen for the interconnects. So going from ECU to ECU, ECU to some sort of switch or storage over a PCB, as well as ECU to some sort of peripheral. And there are certainly challenges that arise when you're going from ECU, any of these applications, to be honest. And that's what this table is showing here. When you're connecting an ECU over several inches of trace on a PCB to a connector, to maybe a few more inches of traces to some other connector, and then to another ECU. So if you can look at this picture here, it's kind of the top portion, just PCB connections. This physical channel loss really starts to add up, especially when you're moving to PCIe speed, PCIe protocol of from 3 to 4, or even PCIe 5.0, which is 16 gigabits per second, or respectively 32 gigabits per second. And if you really add up these channel losses, you're going, you can add up to even 26 to 30 dB of physical channel loss, which is exceeding the loss budget of 28 dB. Beyond that, ECU to ECU over cable, you're also adding up over a longer cable, can be 3 to 10 meters within the car, and that can be 9 to 30 dB on its own, which can easily, again, exceed the channel loss budget for PCIe. Additionally, you may be connecting some sort of peripheral, like a telematics control unit, and the right-hand corner, the far right-hand corner is actually showing not for PCIe 4.0 and PCIe 5.0, but actually PCIe 3 and 4. But still, this is really cutting it close on the channel loss budget as well. So that's where signal retiming, signal conditioning really comes into play in order to be able to use the PCIe. So I'll preface, or I'll set up kind of some of these use cases here, and then I'll pass it off to my colleague Ida. So this is the first use case that I talked about. This is over PCB connections, PCIe protocol, and then adding a signal conditioner. There's a lot of benefits here, which allows for a low latency path, enables multiple connector topologies, is scalable, is an industry standard, and there's a large ecosystem of native PCIe devices. And so what this is showing is really that within an ECU, the use cases that could occur in the future on automotive applications. So this could be adding, more SSD. You can kind of see the indicators here on the right-hand side. These are processor card slots, SSD slots, network slots. And to be honest, this is kind of taken from the data center side of things, but really we're seeing more and more memory being added to a vehicle on board. And so this is one application that we're going to see. We're going to see a large expansion in the future, a large adoption in the future using PCIe in the automotive world, just to be able to support the expansion of SSD. We've also talked about between two ECUs. And these ECUs, again, are labeled ADAS and IVI. But as we're moving to a zonal architecture, this could be just two processors, two central compute processors, or just two processors in general. And this is taking into account a longer cable that could be connected. This could be, 3 meters, which is pretty common in the automotive world, if not longer. And so, again, the benefits of being able to connect between ECUs over PCIe is really that scalable architecture and using that native PCIe that is on many SoCs. The next one that we also talked about is extending that reach still. So 8 gigabits per cable, up to 6 meters of cabling, being able to talk to some sort of peripheral. So maybe not another central compute processor or another hefty processor, but something like a telematics control unit again. This could be your IVI, or your central compute system could be located in the bottom of the car, and then the cabling that's connecting to the TCU, sometimes sitting even underneath the front passenger seat, or even up on the roof by the shark fin antenna. That is, minimum of 6 meters of cable. To be honest, it's probably around 10 meters. And being able to connect natively on the SoCs, but still be able to reach down to the next central processing unit, really is going to, there are plenty of benefits from using PCIe, but will require some sort of signal conditioning solution. So now I'm going to pass it off to my colleague to talk a little bit more about some of the challenges that may arise in some of these long reach applications. Ida?
So, yeah, thank you, Hope. So just to follow up on the items that Hope already indicated about the long cables and the type of connectivity that is required, my segment will focus on what are the challenges of when working with these kind of long reach cables. And there are three elements that needs to be taken into consideration when going into this long reach connectivity. One is, of course, the harness that was mentioned earlier. There is, of course, higher channel loss, higher insertion loss, but there are also implications on the return loss due to inline connectors that are usually part of these harnesses. And this is because there are a lot of limitations and consideration within the vehicle to how to route the cable and what kind of cable types you can use. For example, sometimes the cable need to be flexible because it goes through a back door and needs to be able to withstand the opening and closing of a door or a window or a mirror. So there are different type of cables. Different type of cables that can be used at the same harness in the different segments of that harness. And this need to be taken into consideration when looking at the overall parameters of the channel. And of course, because the vehicle is uncontrolled environment, so there are also, through the lifespan of the car, different elements like temperature, vibration, and other elements that affect the shielding effectiveness of the cable and cause it to degrade. And we can see some example in the following slides. The second element that needs to be taken into consideration is the noise environment. And noise environment in automotive is very, very much different than other more controlled environments as in data centers and others. And it has a very dynamic external noise profile, and it's actually dominated by these external noises, usually bursts that come through different electronic and electrical devices in the car. And we can see some of these and how they are, how are they tested, and what are the implications. And the third thing is the sideband signals, because of the element of that the cable needs to be single cable. So there is a need to handle the sideband signals in a different way in order to be able to work on a single cable. So just an example of how an automotive harness looks like is on the right side. It is considered, the harness considered the second highest cost and the third heaviest component in the vehicle. So it is very important to maintain simple and low weight of the harness and maintain as minimal as possible cable count. And the complexity also impact the actual labor cost of building the car because of the unique connectivity of each of these harnesses, and it's not simple to manufacture and test. And that's also another reason for going to the zonal architecture, as zonal architecture will generate simplified harness structure and shorter cables in some of the segments. These are the automotive cable types that are usually can be found. The UTP, which is an unshielded twisted pair, is seen on the left side, and the shielded twisted pair and the shielded twisted quad or single parallel pair, or that you can see in the middle, and the coaxial cable that is used also in the car. So all of these cables are common type of cables that available, and one of the things that need to be supported is to make sure that when working with the PCIe over long reach, you use one of the common cable uses in the car. Just an example on the variety of these cables, as Hope already mentioned, there is a difference in the type of insertion loss that is associated with these kind of cables. So you can see this is an example of several types of cables, both shielded twisted pair and coax, that are commonly used in car today. This is the insertion loss per frequency at 10 meters. So there is a very big variance between the different cables. And of course, this is dependent on the type of cable. It could be that on the same harness, there will be one segment of two different coax, for example, due to the location that are being routed in the vehicle itself. So when looking at the overall channel insertion loss in this example, needs to take into account that there could be major variance in the numbers. As mentioned, there is an effect of the shielding effectiveness during the lifetime of the vehicle. So in this diagram, you can see that there is a measurement of the gray element is the original new cable that and the shielding effectiveness that was measured. And in the colored lines, this is the cables after passing a fast aging and stressing procedure, and you can see that there is up to 25 or 30 dB decrease in these cables due to this lifespan or emulation of lifespan stressing. So when taking this into account, this needs also to be considered when looking to have a system that will be working properly over the overall lifetime of a car. So Going forward to the second element of the noise environment. So in the vehicle, you have a harsh and dynamically changing noise environment. It is most of the EMC requirements are driven from the regulation 10, and these usually are the tests that are mandated by all major OEMs, and these are the radiated emission support, conducted immunity, and transient immunity. And the baseline of this is defined in the relevant ISO specification, but it is also common that OEM will define its own limits based on its own goals and experience. And there is a large variety between the OEM's requirement depending on different requirements by country or by region or by level of EMC protection the OEM would choose. So as an example, these are the EMC requirements that are needed. And as mentioned earlier, the radiate immunity, it has the specification that the common levels are between 200 and 400 volt per meter, according to the test spec. In a similar way, the conducted immunity is is expected to have 100 to 200 milliampere, and it has different kind of interferences. Either it's a CW or AM testing, and it could be different kind of pulses. The transient immunity is usually very high voltage that is applicable to the cables to see these are imitating different kind of interferences that are being applied to the actual cable from the power. And it also has an ISO 7637 as a spec. This is the type of different interferences that could be tested, and these are like either immediately ramping up a pulse like it's on the right side, or a gradual ramping up of the interference, which is on the left diagram. And this type of noises could be part of the testing and part of the solution that needs to be supported. So these are type of interferences that can be shown in different labs. And the third element is relatively just from functionality perspective. The automotive cable require the signal multiplexing in order to reduce the cable count. And some essential high-speed in-band PCIe signals must be connected over the automotive cable, but the low-speed sideband signals should be either left unconnected or used packetization methods over the automotive cable. The reference clock may not be shared to avoid possible EMI implications. So these were the main consideration and challenges when going over long cables in the automotive. And now I think I will leave it to Anwar to continue the next topic about the short range connectivity. Anwar?
Thank you, Edo. We discussed automotive connectivity that is getting transformed from function-based domain architecture to zonal physical architecture. We have also discussed how PCI Express fits or potentially can fit into interzone, inter-ECU, long reach use cases. In this section, we'll discuss aspect of PCI Express being used for short reach data connectivity. Some of the topic includes that automotive wire connectivity, intra-ECU connectivity, storage connectivity, and scalable compute power. So with the evolution of autonomy in cars, we are seeing increased number of cameras and sensors in each car. For level 2 autonomy and beyond, number of cameras, sensor nodes, and associated real-time data accumulation is growing in exponential rate. So does the need for real-time data processing. Front-end data acquisition from all these cameras and sensors mostly are unidirectional today, and it's likely staying that way as well. The current video acquisition links such as FPD-Link, AFI, MIPI, these interfaces are used today and likely staying. However, the distributed compute nodes and enhanced post-processing are resulting into complex data backbone network that needs inter-CPU bidirectional data connectivity links, both short range and long range. So real-time access to interconnected storage elements is also driving the data connectivity up. The PCI Express organically suitable for handling large data efficiently. The advantage of using PCI Express include it's a native interface for many CPUs, SoCs, FPGAs. It's an organic interface for intra-CPU short and mid-range connectivity, since the interface is already there. The shared coherent memory and storage for distributed processing. The direct PCI connectivity to SSD storages are, a advantageous positioning for PCI Express. The scalable compute power, and lastly, the software flexibility. The PCI Express, software stack, is rich and readily available in different platforms. So this example block diagram is showing data connectivity in a level 3 or beyond autonomous car. But again, the topology can change from one platform to another platform. But this underscores, different zones and how different elements in a zone or inter-zone they can be potentially connected. So some of the applications for PCI Express could be storage, as we discussed and we'll discuss, multiprocessor and enhanced functions, whether that function is within an ECU, somewhere else, within ECU in a different board, but PCI Express can provide a native, already readily available, connectivity for the automotive platforms. So as we had discussed, the huge growth in data acquisition and processing, ECUs or electronic control units are getting more complex and packed with functionalities. One can imagine compute boards will interconnect network through a backbone, as shown in this illustration, similar to what you see in a data center connectivity. Data centers use PCI Express to be its base interface for interconnect. We believe PCI Express inherently suitable for these kind of intra-ECU connectivity. In this illustration, we are showing an example, how compute and storage elements will be connected to each other, how they could interconnect for shared data processing. In practice, actual connection can vary, but it's giving you an illustration, how different elements can be, connected to each other and how PCI Express can fit into, such use cases. And some PCI Express architecture provides most efficient connectivity between CPUs, SSCs, and FPGAs. It enables the scalable compute power with added cards into a backplane. It provides the PCI links are contained within the ECU, and the connectivities are typically short or medium range. Traditional interconnect channels are applicable here, such as traces, flex cables, backplane, with known link loss. Some link, especially the medium range link, may require signal conditioning, such as Redriver retimer, to extend the reach of the connectivity. So as data processing need increases, so does the need for storage capacity. Storage elements are expected to be distributed, hence the need for shared access by ECUs. PCI Express provides the greatest flexibility for shared memory storage access through PCI Express network with minimal latency. In automotive use cases, storage elements using hard disk probably is not very reliable and suitable, as it has mechanical spinning. An SSD actually gives a very advantageous storage element for automotive, and it is being used more and more. And storage is moving towards more like eMMC, UFS, to PCI Express and NVMe based SSDs. The cars are becoming, truly servers on wheels. While automotive platforms need vary from one to another, the complex server compute node topologies will become more common in cars, plus the need for redundancies and diagnostic capabilities. OEMs are expected to adopt a common architecture with scalable compute power, so that they can use a kind of hardware or topologies or elements between different car platforms, with flexible CPU counts, ECUs, cards, and connectivity. This block diagram on left illustrates a server topology that can become reality in automotive connectivity as well, in some form. In this topology, multiple CPUs simultaneously processing, increased reliability with CPU redundancy. The modern computers have multiple CPUs with multiple cores each, and we believe that as the data handling requirement is increasing, that probably will become commonplace in automotive environment as well. So low latency is critical. And in this kind of connectivity, the typically links are well defined and loss is also defined, and that can become a significant consideration for when a signal conditioning element is needed. So additionally, multiplexer and demultiplexer, as showing on the right, can provide flexibility for redundant connections for reliability, and sometimes the need for bypass connections for diagnostics, whether for storage or real-time debug, or other purposes. So we discussed the need for signal conditioning function for long reach, medium reach, and short reach PCI Express link. In this section, we'll look into the PCI Express link budget, briefly redrivers and retimers, and an example of reach extension in PCI Express link. The PCI Express link loss budget is shown in this particular table for different link speeds, Gen 3, 8 gigabit per second, Gen 4, 16, and Gen 5, 32 gigabit per second. These link loss calculations are mostly done for server and PC platforms, and automotive use cases would be different. So while short and medium reach link resembles the link inside a server or PC platform, or the topologies are similar, long reach links probably would be quite different. And as Ido mentioned, some of the challenges that we are expecting for long reach links. So we discussed those challenges, and more signal integrity analysis is required, to understand the need for automotive PCI Express based long reach links, and PCI Express SIG will work on it, and we have a automotive work group, and you are welcome to actually join that work group and contribute your thoughts and ideas. How automotive needs can be addressed in PCI Express specifications and topologies. So while PCI Express link training optimizes the TX and RX equalization of root complex endpoints, and it achieves the best electrical link, the need for signal integrity elements such as redrivers and retimers are highly likely at higher data rates, as we also see in other applications. So signal integrity challenges for short and medium range inter-ECU links are similar to server and PC platforms, and so PCI Express is inherent reach enough for many very short reach inter-ECU links, but for some medium reach links, some sort of signal integrity element, such as redriver retimer, probably would be required. And typically, you'll see that short reach and medium reach can be solved by redrivers, and more challenging links, such as long range links, probably will necessitate use of retimers. So here in this slide, we are showing how redrivers and retimers vary or has advantage and disadvantages when it comes to providing signal conditioning solutions for PCI Express links. Linear redrivers are typically suitable for short and medium range, and retimers are typically suited for long range links. But nevertheless, retimers, for example, can be used for short range as well. So redrivers are typically suitable for latency critical links, such as CPU-to-CPU or SoC-to-SoC connectivity. And retimers are typically suitable for more harsher links with jitter, crosstalk, reflections, and skew issues. And on the table, I'm showing advantage and disadvantage of using redrivers and retimers. Typically, a retimer can provide you 2x reach extension, while redriver reach extension is limited. But redriver gives you lower latency, lower power, and low cost option, and retimers are more potent but complex element in the link. So this slide shows an illustration of a PCI Express link in a more for probably server-looking topology, where we are looking at on the left a PCI Express root complex, launching data at 16 gigabit per second. After about 30 dB of loss, we see the eye is closed with a PCI Express Gen 4 redriver that we have tested with silicon, looks like the redriver is able to open up the eye, and even with some loss after the redriver going into an endpoint with PCI Express endpoints receiver, CTLE and DFE, we're able to get quite a bit open eye, that the CDRs and receivers are capable of receiving. So PCI Express, Gen 4, link packet is about 28 dB, and this particular illustration we are showing how redriver can extend that reach to 45 dB. Similarly, retimers also will provide the reach extension, and typically with a higher amount of reach extension, and with a capability of dealing with more harsher signal integrity environments. Okay, so I'll summarize our presentation today. PCI Express, as we discussed, offers many advantages for automotive applications. It is native to SoCs, CPUs, and FPGAs. It offers low latency. It provides reliable interconnect, and it gives the great flexibility of scalability. It provides shared memory access, and lastly, a large software infrastructure is available for PCI Express. In this webinar, we discussed opportunities and challenges for PCI Express technology as interface for automotive backbone and inter-ECU connectivity. We also discussed intra-ECU and CPU-to-CPU connectivity and storage connectivity. So PCI Express, we expect to have key role in automotive connectivity revolution, but there are many challenges that we have to overcome. And I'd like to invite all of you to join PCI Express Automotive Work Group, to share your opinions and expertise, so that we can solve the large amount of data processing need that we will see in automotive platforms for years to come. Thank you.
Great. Thank you so much, Hope, Anwar, and Ido, for sharing your expertise today. Now we'll go ahead and take some time for some questions from the audience. The first question we have is, what is the best fit PCIe generation for the automotive domain, keeping all of the aspects?
Anwar, maybe I can take that question. Again, I mean, what PCI Express generation or data rate we need, it probably is being dictated by, the platform need. But we can share what we are seeing. So we have seen examples of, PCI Express Gen 3 in automotive with, the cable challenges resolved. So we are seeing some adoption in some OEMs. And we also see some processors, they offer PCI Express Gen 4 and discussing towards Gen 5. So, all of those data rates can, solve certain amount of, data processing or data connectivity needs. But probably Gen 3, we are seeing, many of those challenges are overcome.
Hey, thank you. The next question we have is, would optical fiber optics cabling help in automotive?
I'll take this. I think that optical is certainly an interesting idea, particularly for just how lightweight it can be. But I think that there are two main challenges that we would see. And I think this is also, what we see in the data center is the challenges of being in the robustness of optical and being able to sit in an automotive environment under harsh conditions. I think that is a significant challenge that fiber would face. I also think that the heating, the thermals of fiber might be challenging, depending on how fast you're running on the fiber. I think that's always a significant challenge in the automotive world. And so I think that there would be a lot of challenges for fiber in general to be able to adapt to the automotive world. And I think that the traditional cabling that we see and being able to reduce cabling is really where we'll have to go for these future zonal control architectures.
Okay, next question we have. What is the PCI Express solution for providing data and power to end nodes?
So I'll take this one. So I think that without discussing specific products, I suggest that this is something that is possible but needs to be defined as part of the activity now being handled in the automotive working group of PCI-SIG. And I think that this is a kind of topic that needs to be raised there. And there are multiple ways to support this kind of requirement, assuming there is a market need for that. So that's I think the right way forward when defined by the automotive working group activity. This could be solved.
Great, thank you, Ido. Our next question is, will there be an optical cable for PCI Express 5.0 technology?
So Anwar, it's definitely possible, but I think there are challenges that we just heard, a minute ago. I'm not aware of anyone is actively working on PCI Express, Gen 5 optical cable, but it's definitely possible.
Great. Okay. Our next question here. How is the impact of the increase in temperature taken care of in the automotive environment?
So hope you want to answer. Go ahead.
No, go ahead.
I was just trying to say that this is a design. This is a design, specific design implementation, and the temperature environments, depending on the location in the vehicle, are defined. So it is a specific implementer to take notice of this temperature and make sure that the devices are meeting the requirements. In general, when defining in the system the channel definition and similar things, then temperature impacts need to be taken into account as an additional margin that need to be taken care of.
Mr. Anwar, I can add one comment here is that, I think different semiconductor component providers, they increasingly provide more and more semiconductor components that are suitable for automotive environment, automotive qualified, as well as, capability with extended temperature. It's not uncommon to see many, components, such as 105-degree ambient tolerance.
Mm-hmm.
Great, thank you. Next question here on signal integrity. How does vibration have any impact to signal integrity, and how is that addressed?
So Kevin, sorry, can you repeat the question?
Anwar, he said, does vibration have any impact to signal integrity, and how is it addressed?
Yeah, I do not have any specific answer to it. We have to take an action.
Yeah, I think there is a lot of impact. I mean, from a mechanical standpoint, vibration absolutely does have impact, and that is definitely a common challenge. But yeah, I agree that maybe not something that we'd have to follow up outside of this forum.
Great, thank you. So one more question. Can a redriver or retimer be used in a position where you've already exceeded the channel loss budget?
Yes. Well, adding a retimer or redriver is going to help increase your ability to, it's going to add or decrease, should I say, to the loss budget there. So that's going to help you overcome this challenge by adding a retimer or redriver into your signal chain. So absolutely, this should help with the channel loss budget.
Great. Well, thank you so much. That is actually the last question we have time for today. We wanted to thank everyone for attending today's webinar. The slides will be available to download on the PCI-SIG website, and a recording of this webinar will be available on demand, both on Bright Talk and on the PCI-SIG YouTube channel. Once again, thank you to our presenters and to everyone who attended today.